So first we're going to start looking at Lewis dot diagrams, which show valence electrons. So quick little review, valence electrons. Let's look at the two examples here, nitrogen and bromine. How many valence electrons does nitrogen have? Hopefully you're looking at your periodic table and you see nitrogen is in group 5A. So yes, it has 5 valence electrons. Bromine is a halogen in group 7A. So it has 7 valence electrons. And so Lewis dot diagrams simply show the number of valence electrons. Now let's look at something a little more challenging. Titanium. How many valence electrons does titanium have? All right. And so hopefully you were saying 2. Yes, it does have 2. Now, how do I figure that out? Because it's not in a group A element. It's a group B, the transition metals. Well, I have to do the electron configuration to figure out exactly where all those electrons are. So as I go through titanium's electron configuration, I would see 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, then 3d2. The highest energy level, of course, is energy level 4, and there are 2 electrons there. So titanium would have 2 valence electrons. So if I was going to draw the Lewis dot diagram for any of these elements, all you do is use a dot for each valence electron. So in the case of titanium, it would be 2 dots around the element. So step 1, draw the element's symbol. In this case, I've used an X. Then imagine a box around the element, and you don't need to draw this box, this is imaginary, and then use dots to represent the electrons. 2 dots per side on the Lewis dot diagram. So let's take a look at nitrogen. We said it has 5 valence electrons, which it does. And so we would simply put 5 dots around it. Now, the way I typically do mine, and it doesn't have to be this way, is I always start with the first 2 dots on the right side of the element, thinking of the s orbital. Then I put 1 electron on each other side for the p orbitals. Remember those p orbitals, the electrons are going to keep themselves in their own orbital to themselves unless they would have to move to a higher energy level. So then they would pair up rather than move to a higher energy level. All right, what do you think for bromine? So 7, so I'm going to draw 7 dots. So there's my first 2, 3, 4, 5, 6, 7. And so one of the things that we can see from this is we can see how many electrons are needed. So we can see that nitrogen has 1, 2, 3 sort of places where it needs an electron, whereas bromine only has 1. And so that's one of the things that these Lewis dot diagrams are useful for, to see very easily. Because pretty much each atom wants to have a full outer shell or 8 valence electrons. And in order to do that, these atoms are going to beg, borrow, steal, share to do that. As they do that, chemical reactions occur and bonds form, or bonds break. And we're going to take a look at the kinds of bonds today as well. And so again, here's the octet rule. The elements in groups 1A, 2A, 3A, that's the alkali metals, alkaline earth metals in group 3, bromine, aluminum, gallium, indium, are all going to lose those electrons to become positive ions that we call cations. And the atoms in groups 5, 6, and 7, so that's like nitrogen in group 5A, oxygen, sulfur in group 6A, and the halogens are going to gain electrons to become negative ions. Now, however many electrons they gain is going to be their charge. So if we take a look at this oxygen here, you can see 6 dots, not drawn the way I draw it. This was clipped from the internet, but you can see that it has 2 bonding sites there. And so typically oxygen always is going to try to gain 2 electrons and often will have a -2 charge. As these atoms form ions, gaining and losing electrons, they actually form ionic bonds. And so this is a little helpful chart that I use often when I'm trying to figure out the exact charges of various that various atoms would form as they form ions. Again, ions have a charge, whereas atoms are electrically neutral. Hopefully you've got why that is. Because the protons and the electrons in an atom are equal, but when atoms gain or lose electrons, that balance between the protons in the nucleus and the electrons outside is no longer even. And so ions, then have a charge. Positive ions are called cations. Negative ions are called anions. And one of the ways I remember that is I think about the T in cation. That looks positive. I can also think about ants. We don't like ants, so we have negative feelings towards them. All right, so let's take a look at an ionic bond. We've got two atoms here. The first atom, hopefully you can recognize, lithium, is going to lose its valence electron to that atom on the right, fluorine. As lithium loses this electron, of course, it loses that whole second energy level, that whole N equals 2. And so its first energy level is full. And so we could say that the electron is transferred from lithium to fluorine, and they both form ions. Now, this is going to happen because lithium, of course, being a metal, a group 1 metal, has a low ionization energy. It also has a low electron affinity. It is not trying to attract any electrons. Metals only want to do one thing, and that is get rid of their electrons. Whereas fluorine has a high ionization energy and a high electron affinity. It's very difficult to remove an electron from fluorine, but it's also very good at attracting them. And so as this happens, lithium will now become a positive ion. We can say positive or positive 1. Fluorine becomes a negative or negative 1 ion. And as they do this and they have these opposite charges, so lithium with a big old plus charge and fluorine with a big old minus charge, it's the opposite charges, that electrostatic attraction, that will actually keep this compound together. As we name this compound, we always put the metal first, and its name is unchanged. The non-metal negative ion, its name gets changed to an IDE ending. So instead of being fluorine, it becomes fluoride. So this compound would be lithium fluoride. Okay, so ionic bonding, again, just a quick recap, metal and a non-metal. We get the metal loses an electron, becomes a positive ion that we call a cation. The non-metal gains an electron, becomes a negative ion that we call an anion. And that electrostatic attraction, opposite charges attract, keeps them together. Now, as we do these ionic compounds, bonding, we do keep track of those electrons. These bondings do follow the law of conservation of mass that says that we can't create or destroy matter, and that includes electrons. So we do have to keep track of them. And so another way you can do that is with a Lewis dot diagram. You can see here we have sodium with its 1 valence electron, and chlorine with its 7 valence electrons, and that electron leaving sodium and going to chlorine. As this happens, the sodium winds up becoming a positive ion. The chlorine becomes a negative ion, and that's why they stay together. And so this is sodium chloride. All right, how about this one? KCl. What would you say its name is? If you said potassium chloride, you are exactly correct. And so we can just do a quick recap. Potassium, a metal or non-metal? Yes, it's a metal. And it becomes a +1 charge because it's going to give 1 electron away to chlorine. There are some exceptions that we will look at and talk about. And so once again, our metal positive ion is written first. Its name is not changed. And our negative ion gets an IDE ending because chlorine, of course, is a non-metal and it becomes a -1 charge. And so that is how our ionic compound forms. just like the previous example, chlorine does have a high ionization energy, which means it's going to be very difficult to remove an electron from chlorine, but it also has a high electron affinity. It's going to be very good at attracting another atom's electrons, like potassium in this case. The other thing about these ionic compounds is they always have a neutral charge, a charge of 0. And the charge of the positive ions and the charge of the negative ions has to equal out. So let's look at calcium and chlorine. Find calcium on your periodic table. Of course, it's an alkaline earth metal, group 2. Chlorine, of course, a halogen, group 7. And so they would form the ions 2 plus and 1 minus. So together, that's not going to equal 0. If you do the math, 2 plus and 1 minus, not 0. And so in order to get them to combine to equal 0, you'd need 1 calcium and 2 chlorines. And then they would equal 0. And so we write the formula CaCl2 to show everybody that there's 1 calcium and 2 chlorines. And now our charge equals of the compound equals 0. Compounds, just like atoms, have to have a 0 charge. All right, so let's try some examples. What would you say the name for Mg3N2 is? Hopefully you said magnesium nitride, and you're exactly right. How about this one? Notice the metal is always written first. If you said potassium bromide, you are exactly correct. How about this one? If you said lithium oxide, again, you are correct. Calcium sulfide, exactly. Now, could you write the formula for calcium fluoride? We know calcium forms a +2 cation. So it would be CaF2. Now, how did I know that it was CaF2? Well, because if we looked at something like lithium and oxygen, we already talked about how oxygen has those 2 bonding sites. And so it would like to bond with lithium, but it's going to need 2 electrons. So we would need 2 lithiums here, each lithium donating an electron to become a positive ion. And so therefore our formula is Li2O. The subscript 2 there by lithium, and that's what we call that little number down at the bottom of the line, tells us that there are 2 lithiums. We don't have anything with O, and so we assume that it's 1. All right, let's look at aluminum. How many valence electrons does aluminum have? Hopefully you said 3. And so it's going to give those 3 electrons away, as we know, like all metals do, and become a 3+ cation. How about oxygen? Yes, it has 6, so it's going to try to gain 2 and become a 2- negative anion. And so, and of course, that's why it becomes a -2, because it needs 2 more electrons. So what would our formula be here? So now I'm going to show you a little trick. It's called the cross rule, or sometimes called the crisscross rule. Instead of figuring out how many aluminums you need and how many oxygens you need to equal 0, all you have to do is cross those charges. So what you'll do is drop the charges, no charges in formulas, drop the charges and take the numbers and cross them. And so there comes your formula, Al2O3, for this aluminum oxide. How about this one? Aluminum chloride. And again, we just don't put the 1 there after we write that. And that's called the crisscross rule or the cross method. How about calcium and nitrogen? Can you figure that one out? The formula and the name. Hopefully you were thinking, okay, calcium is going to become a 2+. Nitrogen is a 3-. So when I cross those, we're going to get Ca3N2. And the name would be calcium nitride. Now, the only time that this cross rule doesn't work is when you have something like this. Mg with its 2+ charge and oxygen with its 2- charge. If we cross those and got 2 and 2, well, we don't really need 2 magnesiums or 2 oxygens to equal 0. And so we've simply reduced that to the smallest whole number ratio to be MgO. And the name would be magnesium oxide. All right, let's try some examples. Magnesium and nitrogen. What do you think for the formula? If you need to pause the video after any of these examples to write down your formula, please feel free to do so. Hopefully you thought Mg3N2. Calcium and sulfur. And this one is just CaS, calcium sulfide. Aluminum and chlorine, we've already seen. Hopefully you remember that one. AlCl3 for aluminum chloride. Now, take a look at this tin-4. Tin, of course, on your periodic table is a transition metal. And because these transition metals are filling their d orbital, they can sometimes move their electrons around a little bit. Of course, tin's just on the other side of that transition metal. It's SN, atomic number 50. And so, because we can't quickly and easily look at the periodic table and figure out how many valence electrons, we always, for the transition metals, we always use the Roman numeral. And this tells us that this tin, which is SN, that number 4 tells us that this is tin 4+. Oxygen, of course, is always 2-. So what would your formula be there? Hopefully you thought SnO2, and that's going to be tin 4 oxide. Now, occasionally, we're not going to have just 2 elements for a compound. We may have something called a polyatomic ion. And a polyatomic ion is exactly what you would think it is. It has many atoms, and it is an ion. These formulas and charges are basically carved in stone. We can't touch them or change them. We just have to work with them as they are. There is a chart of these on 4.3 in your book. Like, here's an example. Ammonium is NH4 with a +1 charge. It has 1 nitrogen, 4 hydrogens, and it has a +1 charge. And so that is one that you should know. Don't confuse ammonia and ammonium, by the way. Here's some others that you should also know. Carbonate, sulfate, SO4 2-, chlorate, or perchlorate, excuse me, nitrate, and like I said, you'll want to use that list on your book, especially for the homework. All right, and so the polyatomic ions also follow the cross rule. So if we have lithium carbonate, all right, lithium is a 1+, carbonate, CO3 2-. And so we use the cross rule, and so there's our formula. And we don't need that one. We can get rid of that one, there bicarbonate. If there's more than one of the polyatomic ions needed, then we do use parentheses. So like, for example, aluminum and sulfate. Use your cross rule, and we get Al2, SO4, 3. Notice SO4 has not changed. I haven't done anything to it. I simply put it in parentheses and put the subscript 3 from aluminum next to it. All right, let's try some other examples. If you were thinking sodium sulfate, you are exactly right. And like I said, you may want to look at that list in your textbook online. I believe it's 4.3 is the chart number. How about potassium perchlorate? If you were thinking KClO4, you are correct. How about Na2CO3? That's sodium carbonate. Now, where did this 2 come from? That's by sodium. Well, carbonate has a 2- charge. So if I uncross it, I can go like, oh, okay, there's carbonate with its 2- charge. How about lithium phosphate? If you said Li2PO4, I actually don't have the list in front of me right now, and I think that is actually supposed to be 3. Because lithium phosphate is 3-, not 2-. So I apologize for that error that I did not catch earlier. Barium hydrogen carbonate, HCO3, is hydrogen carbonate. How about this one? If you're thinking calcium bromide, you are exactly correct. Here's another one. Notice this transition metal here. So if you were thinking, nitrate is NO3 with a -1 charge. So that means that this 2 down by nitrate, this subscript of 2, came originally from lead. So that means this lead must be a 2+. It's a transition metal, so we need to tell everybody its charge. So if you're thinking lead 2 nitrate, you are right. Okay, so just a couple things on the properties of these ionic compounds. It is a metal and a nonmetal. Typically, they have a crystalline structure. The smallest piece that you can have of an ionic compound is called a formula unit. They are pretty strongly bonded together because of the opposite charges that attract each other. They also have high melting points. Covalent compounds, on the other hand, are only nonmetals. So that's pretty easy because there's only about 15 on your periodic table, all on the right side except hydrogen. The smallest piece of a compound that's covalent we can have is called a molecule. So that's a very specific term in chemistry. Covalent compounds share electrons. The way I remember that is sharing is caring. They can be polar or nonpolar, which I'm going to tell you about, and they have low melting points. So let's jump right in with these covalent compounds. These covalent compounds, again, nonmetals sharing electrons. So if we take a look at a Lewis dot diagram for hydrogen, or 2 of them, each with 1 valence electron, they would share that valence electrons. Now, this covalent bond is like a shared agreement. My husband does this with a bunch of his friends with tools and stuff. Like, hey, I'll share my chainsaw with you if you share your trailer with me. And so at any given time, the chainsaw and the trailer may be at my house or his friend's house. You never know. And that's the case with these electrons. As they're shared between these 2 hydrogens, they're going to move around both hydrogens pretty evenly. And so each hydrogen now kind of looks around itself and does a little inventory and says, okay, how many electrons do I have? Oh, I have 2, is what it would think. Another way we can show that, instead of using the 2 dots, is we could use a line. And that line, on the end of each side of that line, there is an electron. So that is our electrons there. If they were sharing 2, each atom was sharing 2 electrons, we would draw 2 lines for a double bond, and that would be 4 electrons shared. If there were 3 electrons being shared, we would draw 3 lines for a triple bond. And we're going to look at some of each of those. Now, as we take a look here, chlorine would do this. Chlorine gas, we would actually call it dichloride because there's 2 chlorines. We need that IDE ending here. And you can see they're sharing those electrons right here. So there's 1 from this chlorine on the end of this line and 1 from this chlorine. So that's 2 shared electrons. These electrons here that are not part of the bond, and we are going to talk about them, they actually have a name. They're called lone pairs of electrons. and they're not going to do anything. And each chlorine has its own of these particular electrons. So there's a single bond, again, 2 shared electrons. And each chlorine has 3 lone pairs. Here's nitrogen with a triple bond. How many shared electrons in that triple bond? Hopefully you're thinking 6. And so what each atom does here now is each atom looks around itself and says, okay, do I have my octet? Let's count them. 2. So that'd be 2 in this first bond, 4, 6, and then each atom has a lone pair over here, making each atom believe that it has 8. And then these electrons are going to move around each atom, sort of, and spend equal time around each atom of nitrogen. This is why nitrogen makes up about 78% of our air, because of that triple bond. It is so stable. Here's an example with a double bond, carbon dioxide. And you can see another vocabulary word for you besides lone pair. You can see that our carbon goes in the center, and we typically call that the central atom. When we're writing the formula for CO2, the atom in the center typically goes first, and it's the one that we typically have the fewest of. But you can see these 4 shared electrons, 2 from carbon, 2 from oxygen, and when each atom looks around itself like this carbon right here, it counts up and it says, okay, 2, 4, 6, 8 electrons. And so it thinks it has 8 valence electrons. All right, so how do we draw these Lewis dot structures for compounds? Well, it can be a little bit tricky. So here's my tips and suggestions for you to do that. The first thing you need to do is figure out how many valence electrons each atom has. Count them all up, total them all up. Then figure out which atom you want to put in the center. What would be your central atom? Again, that's typically listed first, and we have the fewest of them. Then draw single bonds between the atoms to form the molecule. Remember, each single bond counts as 2 valence electrons. And then put all the remaining electrons around the other atoms until everybody has their 8 or octet, except, of course, hydrogen. Hydrogen would be the exception because it only wants 2. All right, so time for you to practice. SO2. How many valence electrons are there? S in group 6. O is also in group 6. So I get a total of 18 valence electrons. All right, so what's the center atom going to be? The atom in the central atom. If you're thinking S, I agree. All right, so now let's put the S in the middle and draw those bonds. Keep in mind that as we do that, we had 18 valence electrons, and now we would subtract 4. We're going to subtract 4 and have 14 valence electrons because this is 2 valence electrons and this is 2. So after we put in those bonds, we now have fewer electrons to worry with. All right, so now that we have 14 left, we're going to put them in as lone pairs. So let's take a look. 2, 4, 6, 8, 10, 12, 14. Does everybody have an octet? So let's take a look. What do you think? Does this atom have an octet? Yeah. How about this one? This sulfur in the middle. Does it have an octet? 2, 4, 6. Uh-oh. No. Well, let's take a look at this oxygen. Does this have an octet? 2, 4, 6, 8. Yes. And since our sulfur in the middle does not have its octet, one of the lone pairs can become a double bond. And that's how we know when a double bond occurs. And so now take a look at it. Now does every atom have an octet? Yes, they do. So yes, this would be the correct Lewis structure. Now, you're probably thinking, well, wait a minute. I put my double bond over here. Is that okay? Yes. If you put your double bond over there, that is perfectly fine. And that's one of the things about these atoms is they share electrons. There are multiple ways of drawing these, multiple correct ways, I should say, of drawing these models. All right, here's a couple for you to practice: carbon tetrahydride and phosphorus trichloride. All right, so how did you do? Did you start with your total number of valence electrons? Come up with 8 for CH4? Come up with 26 for PCl3? Did you figure your central atoms, C and P? Did you put in bonds to have the other atoms around the outside? So hopefully you got CH4s looking something like this. No lone pairs of electrons here. There were only 8 electrons to start with, and each of those electrons was used in a bond. So there's 2. Here's another 2. Here's another 2. And here's another 2. So that's my total 8 valence electrons that I had. All right. How about PCl3? Did you come up with something like this? And so once again, here's 2, here's 4, another 2, 6, and then hopefully you came up with lone pairs on each of these, because for this PCl3, you should have had 26 valence electrons to start with. So as I put in those bonds, that was 6 electrons, so I have 20 left. So I did 2, 4, 6, 8, 10, 12, 14, 16, 18. Now, did I know that that was going to work out? No. All right, well, 20, because phosphorus doesn't have its octet, and it just so happens to work out that I'm able to get both Lewis structures drawn. All right, now, because these Lewis structures can form in multiple different ways, carbon and oxygen, like, for example, can bond with each other. Like, one carbon can bond with one oxygen, but one carbon can also bond with 2 oxygens. And so when we identify what compounds we're talking about, we need to be pretty specific. So what is CO? You probably already know. It's carbon monoxide, but CO2 is carbon dioxide. And so what we do when we're naming covalent compounds is we use prefixes to let everybody know that this is 1 carbon and 1 oxygen, or 1 carbon and 2 oxygens. And so these prefixes become pretty handy. And here they are. You might want to snap a picture of that. These also come right from your textbook so that you can see how many atoms are present. All right, and so if you take a look, here's some examples for you. Nitrogen monoxide, but N2O4 is dinitrogen tetraoxide. The only prefix that we don't use is mono in the front. So if the first element, which is often the central element, only has 1, notice there's no mono here because we don't use mono at the beginning of the name. And then, of course, you might have to mess with the vowels a little bit, dropping one of the vowels so you don't have monooxide and tetraoxide. All right, so hopefully you feel like we've accomplished everything I'd hoped to do. Hopefully you now know about the octet rule. You can draw Lewis structures. You can define ions, cations, and anions. Hopefully you feel like you can write and name simple ionic compounds, and you can discuss the properties of ionic and covalent compounds. Hopefully you could also feel like you can define ionic bonding and covalent bonding, their characteristics, and distinguish between them.